So, welcome to my talk on anti-picking features of high-security locks. Who am I? Well, I'm the Secretary of the Open Organization of Lockpickers in the UK, and I'm a lock design fanatic who has been grappling with the problem of how to design an unpickable mechanical lock for about the last half a decade. Why am I giving this talk then? Well, I'm giving the talk with the hope that maybe if I run through a lot of ingenious attempts to solve the problem, other people will be inspired to grapple with the problem themselves, and maybe they'll see something they think they can improve upon, or if nothing else, just to show you some very cool lock designs. In order to do this effectively in this talk, the problem is that I'm going to have to talk about lockpicking in a very abstract way. And the main reason for that is I'm covering such a broad variety of locking mechanisms that it's simply not going to be possible to talk about this in the same way that you would talk about picking conventional pin tumbler locks. So I'm going to abstract this out to kind of the very fundamental concepts in lockpicking, and then we will attempt to apply those to the locks, hopefully in an effective way. So first of all, we have manipulation. Manipulation is basically just the idea that we need to be able to move the components inside the lock. If we can't move the components inside the lock, well, then we're not going to be able to get it open without the key. Secondly, we have tension. So this hinges on the fact that we can't produce elements in a lock perfectly. They won't all be identical. So if we can apply some kind of driving force in the open direction, then we will get contact against those blocking elements inside the lock, whether they be levers or wafers or sliders or discs or pins or whatever it may be. Then when we've got that kind of that force, which is what I'm referring to as tension, then we will be able to get some kind of information out of the lock. So I have to be able to do both those things at the same time. We will see some locks that have ingenious mechanisms to try to prevent you from doing them both at the same time, although you could do either one relatively trivially on its own. And of course we're doing all of that in order to get information out of the lock. So when we're able to apply tension and manipulate the mechanism, typically we will be able to get feedback from the mechanism, although some locks attempt to make that impossible, even if you can do both simultaneous manipulation and tension. We are not considering drilling, snapping, cylinder or dial pulling, angle grinders, excessive torque, melting, thermal lances, explosives, liquid nitrogen, or chemical attacks, or any other destructive attack. That is a different problem. For some high security locks, they will use a relocker. So this is a sacrificial portion in front of the lock. And if you were to destroy this sacrificial portion, say using any of the aforementioned methods on this slide, you will trip the relocker mechanism and the whole thing will brick itself, whether that be a vault door or a safe or whatever it may be. So these are not a quick way to get through all locks, particularly high security implementations. But secondly, although these are things you may wish to consider when designing a high security lock, just keep in mind that is not always something that is a priority for the locks that we'll be looking at today, simply because this whole problem can be shifted elsewhere and doesn't have to lie on the lock. We are also not considering direct cam actuation, overlifting, bumping, snap guns, tryout keys, wrapping, jiggler keys, impressioning, self-impressioning, decoding with a visual, audio, or any other method, X-ray attacks, or ultrasonic attacks. These are all attacks that you will want to consider if you are designing a high-security mechanical lock. But realistically, this talk will be too long if I try to cover all of these things. So instead, I will focus on lockpicking because it is, in a very narrow sense, because it is probably the best known and probably the best understood of the attacks. You can ask me about any of these other attacks in questions after the talk. So, first off, the most common attempt to make unpickable locks has hinged around the idea of making the mechanism impossible to manipulate. So the kind of earliest examples that we had were heavily warded locks. And this was an incredibly effective technique back when there were only a tiny handful of people who had the required skills, knowledge, equipment, and so on and so forth to manufacture these locks and the corresponding keys. So here we can see quite an intricate example of a warded lock, and you can see that essentially the way it works is if you have a key cut with a matching pattern, then it can pass through these wards, hence the term warded lock, and the rest of the mechanism is essentially just a single lever that once lifted allows the bolt to move. So essentially if you can get something sufficiently long through this through the obstacles and the wards in this lock, then you will be able to retract the bolt and open the lock. Today that doesn't work so well just because manufacturing has kind of moved on a bit. Here's a modern implementation of basically the same principle. It still survives today. This is a heavily warded lock designed by UrbanHawk, but in a pin tumbler design, and it features a very paracentric keyway. So this is a keyway where there is basically no straight line that you can cut down the middle, and there is no pick thin enough that will have free travel up and down inside that keyway. But this is a relatively basic attempt to prevent lockpicking attacks. As much as I respect all of the work UrbanHawk has done on his design, so we shall move onwards to a more complex design. The previous design is very effective at warding things in terms of your pick movement left and right and up and down, but of course the lock would be more secure if we could also create some kind of warding as we travel into the lock in that third dimension, and that's exactly what the Lay's chain key lock attempts to do. This works as a conventional pin tumbler lock, except the key is made of lots of little segments that are hinged together, and the key is injected into the lock, which allows it to then travel around these 3 dimensions of warding as you go into the lock. A much earlier example is the Schneckenschloss, which translates as snail lock from Germany, I believe. Here we have a thin key that winds in through an obstruction at the front of the lock, which we can kind of see that on the left-hand side here, that obstruction. And so again, there's no straight pick that you could push into this lock in order to set the elements correctly. Here's another example of kind of this idea of creating heavy warding, although this time not in 3 dimensions. What we have here is the Tan Reliance, which was an 1800s bank lock. And the key feature here is that, so this was a lever lock with lots of levers kind of shaped like this, but the special feature here is this is a lever lock that has this half-moon shaped piece of warding that's actually attached to one of the levers. And we can see that that would fit then this L-shaped cut in this key. And the problem that you've got here is that traditionally, if you were going to attempt to pick a lever lock, well, you have a wire that simulates typically the end of the key, and that gets inserted into the lock and is used to try to retract the bolt. And when the bolt stump then presses against the levers, we would use another pick wire in order to manipulate those levers into the correct positions. But that is an L-shaped wire, and that would simply not be able to get around this L-shaped ward. So we'd have to come up with some more complex design, possibly involving multiple pick wires with intricate bends in them in order to get around that L-shaped piece of warding inside the lock. Here's a modern implementation of the Tan Reliance, albeit done much less well, using a pin tumbler mechanism. And then again in a slightly different direction, but still in the same theme, we have the Vormald meter lock. So this was used on gas meters in the UK, and essentially the principle behind this is the same rough idea as what makes the SOFA problem in mathematics challenging. The SOFA problem is essentially this problem of designing a shape that's quite good at getting around a right-angled bend in a corridor. And so we have this large cylindrical obstruction right at the front of this lock, and the Vormald meter lock key has a moving tooth in the end of it, basically. And so that retracts as it travels down the channel, and then it extends once it's inside the lock and is able to set the single lever inside this lock and open it. However, from a picking perspective, if you don't have a tool with a moving end, then you run into quite a conundrum. You can either have a pick wire that is long enough to lift that lever into the correct height, but then it won't fit down that cylindrical channel, or you can have a pick that does fit down that cylindrical channel, but then it won't be long enough to set the lever at the bottom. Then we have the Rosengrens 32A81. So this is a Swedish lock designed by the Swedish safe company Rosengrens, and it uses a curtain to protect the discs inside. So the way this mechanism works is it has a large number of discs inside that need to be rotated to the correct degree, and if that is done correctly, then the gates cut into them all aligned to make one nice long slot, and there is a bar that can drop in what is called a sidebar mechanism in order to allow the lock to open. But most disc detainer locks do not feature a curtain. A curtain is this piece of movable warding in the center of this lock. This turns one-to-one with the key, but it makes it impossible to insert any kind of conventional disc detainer picking tool. Then we come to the Abloy Classic. This is also a disc detainer. This one has a very iconic half-moon shape. This is a Finnish design, and this was considered very, very difficult to pick for a very long time. But the key here, the reason why it's so difficult to pick, is we have a half-moon shaped opening in the front of the lock, but in terms of the possible configurations of discs, a minimum movement disc does not move at all, and a maximum movement disc has to move 90 degrees. And it turns out it's incredibly difficult to design a pick that is both capable of turning one of these discs 90 degrees, and yet is small enough to fit through the remaining gap if you find yourself unfortunate enough to be faced with a maximum and a minimum cut disc right next to each other inside the lock mechanism. Huxley Pig has written a paper on this where he goes into much more detail on exactly how this works. I highly recommend reading it if you can find a copy. And then finally we get onto the Comforti safety deposit box lock. So this is used for safety deposit boxes. That's why we have two openings for keys here. We have a one on the left, and we have this much more complicated mechanism on the right, and we will be focusing on the mechanism on the right. What's curious about this is we have these two levers that are connected together like a jigsaw, and while it is relatively trivial to set this the upper lever, that's not too difficult at all. The problem is that the bolt stump that wants to enter the gate in the top lever is attached to the same piece of metal as the bolt stump for the bottom lever for each of these lever pairs. And so once we set that top lever and the bolt stump for the top enters that gate a little bit and helps hold that up in place, we then attempt to set the lower lever. But this curve on the edge of this lever is very cunningly designed, so that as we get closer and closer to the gate on the lower lever, what we find that we are pushing backwards against that bolt stump. And if we want to set it correctly, well, we're going to have to allow that bolt stump to move backwards a little bit. And the problem there is if we allow that to move backwards a little bit, well, we release the lever above, and then they both drop, and then we have gotten nowhere. And so with any conventional picking tool, you will be caught in an infinite loop of set top lever, attempt to set bottom lever, and as you attempt to set bottom lever, release top lever, resetting the whole thing and having to start over. So now we come onto designs that attempt to make it very difficult to apply tension to the mechanism, even though it might be quite easy to reach the various components and move them around. So the first example we have is the van lock. This is a tubular lock, and we can see the 7 pins there. And what's curious about this is the 7 pins come flush with the face of the lock. And so this means there is basically no surface to grasp or gain purchase on to apply tension to the lock. The way the key does it is it has prongs that stick into the pin channels, which sets them to the correct depths, but then is also used to tension off. And since some of the possible pins that can exist in a van lock include zero movement pins, so pins that must not be moved at all, it can be actually quite challenging to pick this lock using any conventional method. We then have the gold atoms. This is a very cheap Chinese-made padlock, but it has a very curious mechanism. It uses a reverse sidebar mechanism. And the way a reverse sidebar mechanism works is it has its own springs that bias it constantly in the opening direction. So we don't have to apply tension to this lock because it is constantly trying to open itself. The problem arises that the pins that have the gates in it for this sidebar to drop into, they also have their own springs, and those springs are stronger than the sidebar springs. So we are unable to tension the lock in any conventional way, and because of that, when we set any pin to a correct height, and it's not very difficult to reach the pins, the problem is they won't stay there, because as soon as you set one, you have no control over the amount of tension. The lock tensions itself entirely on its own terms. And so as soon as you move on to manipulate another pin, well, that first pin drops back down again. And this applies to any one of the pins, and it doesn't matter whether or not it would be correct in the binding order or not. There is simply no way to progress unless you can find another way to apply tension to the mechanism. Unfortunately, that image hasn't loaded, which is a little bit awkward. But I've got this image. So the Uema 750 is an interesting mechanism. So this is a Chinese-made Eurocylinder as well. This one is a little bit more fancy. It is again a reverse sidebar mechanism, but this one actually uses a reverse sidebar in two parts. And the benefit of that is in this particular configuration, if you attempt to tension the lock, it will just spin round and round and round and round and round and round. And the way it achieves that is it has a front portion to the plug, and it has a back portion to the plug. And only when this reverse sidebar mechanism, when both parts of the reverse sidebar mechanism are allowed to drop inwards by having the sliders correctly aligned, can the front part be locked to the back part and therefore open the lock. So here we can see the lock with an incorrect key inserted, and we can see that we have these silver sliders which have this V-shaped cut in them, here not correctly aligned. We have this lower portion of the reverse sidebar, and we have this little upper portion of the reverse sidebar that is sitting above the shear line outside the outer circumference of that plug. And so when we turn the key, or turn the plug with the wrong key inserted, well, nothing happens, essentially. However, if we insert the correct key, as we can see here, we see both parts of the reverse sidebar mechanism do drop in, and then what happens is the cam moves, and we might be able to see that up on the top left-hand side of this here, that actually turns. So that brings us on to the crankshaft lock, and this is a lock that I had quite a bit of trouble categorizing, but I think I've settled on leaving it here. This is a concept. I don't, to the best of my knowledge, it's never been produced, or at least hasn't been produced yet. But it's a 10 slider lock. These sliders are these little reddish pink portions we can see over here, and they have gates in them, and when all those gates are correctly aligned, this sidebar can drop in. The thing that's difficult about this lock, though, is it's not very hard to see how to tension it. We just need the correct tip on the end of our tool and just turn that in order to apply tension to the mechanism. But the problem is, if you design a tool with a straight shaft, well, it's very likely that that's just not going to fit into the lock, as we can see on the right-hand side here with this convenient diagram. There is no straight line down the center of this lock to get there. And the problem with just creating a curve, as we can see with this illustrated potential tool, well, we don't know what the curve has to be. The curve is entirely dictated by the slider positions, and we can't know what the correct positions on the sliders are until we can apply tension to the lock. So that's another very clever design. That brings me on to the chroma protector, the penultimate lock in this portion. This is a lock I have given a talk on at the DEF CON Lockpicking Village last year. There's also a talk that Jago Fagerlund has given a talk on, a much better talk entitled The Unpickable Chroma Protector for OzSecCon, and I highly recommend watching his talk if you're interested in this lock mechanism. The interesting thing about this lock is that it is a wafer lock. I have often seen it categorized as a lever lock. That is certainly not correct. But I guess the reason is because most people don't believe that one of the most secure locks ever designed is actually a wafer lock. The thing that is particularly secure about this wafer lock compared to conventional wafer locks that you will see on low security cabinets and that sort of thing is that the wafers look like this, and the key only can apply tension to the core via the wafers. And so what's unique about wafers is if you have a wafer lock that is designed in this sort of configuration, then you can make it impossible to tension the lock without first having aligned at least one wafer. So in this case, what we would see is that the key is going to be longer at any given portion on one side than the other, and as we turn that inside the lock, the longer side will make contact with the inside of the wafer first, and that will result in a lateral motion, a side-to-side motion. Pardon me. In a lateral motion first, until the other side of the key makes contact with the other side of the wafer. So that's what we see when the lock starts to turn, because at that point the wafer can no longer move side to side, it is jammed in place by the key, and so that rotational force in the key is then transferred to the wafer, and that is then transferred to the core, which is that blue portion that you're seeing there. Of course, if that weren't intimidating enough, this is the border panzer design. That is the exact same sort of mechanism, but this time it features wafers that slide left and right and up and down, and the key features 4 beards. So this is phenomenally complex to pick, and unfortunately very rare. A much simplified and much smaller format designed on the same principle is the Chubb AVA. This is a very small wafer lock that is occasionally found in the UK, and it works on the exact same design principles, just with fewer options. And that leaves me finally to the drive cam mechanism that you can find in many safe locks, not just many combination dial safe locks, not just this model 6741 made by Sargent and Greenleaf, but this is the one I happen to have, so this is the one I will be using as an example. What we have here is we have a number of different wheels, which are these silver portions that have a gate cut into them. And this strange lever-shaped thing actually hides a bar that rests along those levers. And when the gates in the wheels are, when the gates in those wheels are correctly aligned underneath this this nose portion, then it can drop in and open the lock. And you might have noticed that there's a little corner of a spring here on this lever, and that constantly biases the lever against the wheels, so the mechanism is constantly under tension. But the problem that we do have is this black portion, and forgive the fact that the camera angle changes slightly here, this black portion moves 1-to-1 with the dial, and it's necessary to move that before you can move any of the wheels. And so the problem is, in this position, the nose drops in slightly, because it has space, it matches the gate in the drive cam, and so at this point we have tension against the wheels, but anywhere else that we move this drive cam, the drive cam causes the nose to lift up, or the lever to lift up, and at this point there is no contact against the wheels, and so there is no way of tensioning the mechanism unless we are inside that little gate in the drive cam. But unfortunately, that also means that we only have any tension against the mechanism for a tiny portion of the dial. That brings me on to mechanisms that attempt to prevent simultaneous tension and manipulation. So we are typically looking at blocking mechanisms here. The first, and for those that are aware of blocking mechanisms, perhaps one of the most famous examples is the Western Electric 30C. This is an American payphone lock, or was an American payphone lock. And what's curious about this is it's a lever lock, and the way that it works is we have a bolt stump that needs to come across and test the levers, and we can move the levers as freely as we like, but when we apply tension before the bolt stump can come across, this serrated lever grabber interacts with the points on the tips of the levers and immobilizes them. So here we can see the gate on the levers, and we can see the stump trying to enter that, but we can also see the lever grabber has already grabbed all of those levers. So we can move the levers, or we can apply tension, but when we apply tension, the levers are immobilized and we can no longer move them. So that makes picking this lock phenomenally difficult. We also have the Fichet 787. This uses a very complicated mechanism. I've coloured in the patent diagram that I've found on Lockpicking, and essentially this red portion is the key. The key directly interacts with some levers. The lever then turns a gear. The gear has a gate, and here on the left-hand side we can see all those gates aligned. And then before the gates and the wheels are tested, there is a blocking mechanism, which is this kind of blob to underneath the orange gear that has to engage with the wheels or the gears before they're tested, again preventing them from being rotated, which again makes it very difficult to pick the lock. The Abloy Protec and Protec 2 are also locks that include a blocking mechanism, although this time in a disc detainer format. The NATO Mersey lock, on the other hand, uses a slightly different mechanism to achieve its blocking, which I will attempt to explain. The curious thing about this is, so this is a 14-lever lock that normally features two sets of levers, but what we see here is we see only a single lever, and this has been set up so that it's much easier to kind of illustrate the way the mechanism works. So thank you to Automaton for that. We have this kind of strange element here with a nose and a pivot, which is this portion here. We can see the corresponding one up here as well. That's the pivot for it, and there's the nose on the end of it. And here we can see that there is a pivot for the levers, and the pivot for the levers is inside this pivoting portion itself. So when we apply tension to the lock conventionally, what happens is these two stumps, which are attached to the bolt, they just move nicely into the gate when we use the correct key, and the lock opens totally normally. However, if we apply tension and everything is not already in the correct position, then what happens is the bolt stumps press against the levers, and the levers press against their own pivots, and the pivots then cause these elements to move. And when they rotate around their pivots, they drop this kind of nose into a corresponding slot inside the bolt work and immobilize the bolt. And so when you attempt to tension the lock in the open direction, then what you find very quickly is none of the levers are binding up, and instead you are basically just blocking the bolt with these two noses, which makes this lock phenomenally difficult to pick. More recently, we've had Shane's Stuff Lock, which I believe is about sometime late last year, where Shane, who has a YouTube channel where he does all sorts of interesting engineering projects, he thought he'd turn his hand to the problem of creating an unpickable mechanical lock, and by his own admission, it was much harder than he thought it would be, which I find validating. But essentially the way his lock worked is it would set the pins to a given set of heights, and then it would immobilize those pins, and then as you turned the key you would lose access to those pins, you could not reach them, and then the pins would be tested against a complex kind of series of warding. I highly recommend watching his video because he does give you a much better idea than I can of how his lock works, and it's quite fun. That leaves us with locks that attempt to deaden feedback, despite perhaps being able to tension them or manipulate them. So, coming back to the Sargent and Greenleaf 6741, this is a combination dial safe lock, and although it's quite tricky because you can't really tension the mechanism very easily, it turns out that is not a completely impossible lock to manipulate. And so there are various combination dial safe locks, which, while having the benefit that that they largely dictate how you can interact with it. So you don't have a keyway, you can't insert your own tools. You basically only have the option to turn left or right on the dial. They have then, on top of that, attempted to incorporate mechanisms to make it very difficult to get any feedback out of them. So one of these is another lock made by Sargent and Greenleaf. This is the 8550, and the way this works is, well, you're going to have to look past this large silver sprung element, but we again have a drive cam, this time in a brass color. We have our wheels, which we can see behind here, largely aligned. We have this curious little silver portion attached to the drive cam, and we have this rather odd silver thing attached here as well. And you can see behind that there is also what looks to be, and is, an otherwise largely normal lever nose. And the thing that's curious about this is, in this particular position, the lever is held up by this spring and is not touching the wheels. But as we turn the drive cam, this silver portion will make contact against this slope, and it will push the this silver portion up over this little ledge, and it kind of clicks in above this ledge, and it's held there. And what that does is it basically stores a lot of kinetic energy in this kind of spring, and the drive cam itself can actually move front to back, so kind of depth-wise as we look into the picture, and that means that the mechanism can be released. And if it's in the wrong position, well, then it will bring the lever nose down. The lever nose will test for a moment of a second, but then it will effectively bounce off the wheel pack. And so you only have that momentary fraction of a second to get any information out of the lock before the lever is once again raised off the wheels. If you've aligned everything correctly, then as it fires fully all the way into the slots in the wheels, and you can then retract and open the lock. Similar mechanism, also by Sargent and Greenleaf, is the clock. It has a few other names as well, which I have unhelpfully not included. But again, this is a similar sort of mechanism. We have a silver lever of some kind now. We have some brass wheels hidden behind this plate, and we have a very curious looking drive cam. The drive cam includes a spring, and essentially what happens is, in its default position, it kind of looks like this, and so there is no gate to be found. As it turns, what we find is it will wind this mechanism, and we actually get the gate revealed for a moment. And again, if we're very lucky and everything is perfectly aligned, well then the lever nose will be able to drop into that gate, and it will prevent this clever cam mechanism from then immediately concealing the gate again. And if we did not get everything correct, well then what happens is that the lever touches down against the wheels for a moment of a second, and then the sprung element that is released immediately pushes it back out of the way, and we get back into this position here where there is no gate and we have no information. And then we have the Manifoil Mark IV, so this was a British Ministry of Defence lock, and it uses a cunning two-part drive cam. So This drive cam actually has 2 levels to it that need to be aligned in order to create the gate, as we can see here. But it also has these 2 rather devious rollers that make it very, very difficult to tell the difference as to whether or not you're trying to get information from the nose on this lever, which is actually useful, or if you're just working with one of the 2 specially designed rollers. That can be very, very tricky to work out indeed. And then finally, I'm going to bring you on to some special considerations. It turns out my categorization method is not perfect, and I was unable to categorize every high security lock that I wanted to. So I thought I would take a look at some special considerations that don't fit my schema, but nevertheless have some interesting value that we might want to take a look at. So, first of all, we have the Chubb detector. This was the unpickable lock of the 1850s roundabouts until it was picked in the 1850s. And the way this works is there are lots of implementations of the Chubb detector. It has a very long history, but essentially this is a lever lock. But what's curious about it is we have this little pin that sticks out of this lever, and this pin rests across all the other levers that would be laying in front of it. And what happens is essentially if any of the levers ahead of it is lifted too far during a manipulation process, then it will trip the detector mechanism. So here we can see the detector mechanism is tripped. So what's happened is this lever has been lifted too high, and this small sprung portion has then slipped over this little lip, and it then jams in place and prevents any movement of the bolt in the opening direction. If, on the other hand, we press in the closing direction, then we are able to once again reset the lock into this position. So the lock is not bricked, as it were, if someone attempts to manipulate the lock, and anyone with the correct key can once again reset the mechanism and then turn the key in the opening direction in order to open the lock. But this kind of trap mechanism does make picking very tricky. For those who have not yet seen it, Seth Gould's coffer, as filmed in Forged and Filed, which is a video you can find on Vimeo, this is an absolutely stunning video. Seth Gould spent 2 years constructing this kind of medieval style coffer, and although I can't show you it very easily, essentially I believe there's something like 11 steps to opening this coffer, even if you have the correct key. So having the correct key on its own is not sufficient. There are a whole series of hidden buttons and switches and steps where the key has to be turned only 90 degrees, and then it will allow something else to open, and so on, that are required in order to open the coffer. And again, you know, you could be able to pick the mechanism, but that wouldn't necessarily result in the lock opening. Then we have the RKS, the RoboKey Systems design. This is a tiny, tiny combination lock, and in its kind of final form, at least as far as it has today, it only has 5 wheels. But the whole idea behind the RoboKey Systems design was to have a large number of combination wheels. So you essentially have a very complex, well, not a very complex, it's quite a simple combination lock, but it is one that will take an incredibly long time to dial. And the RoboKey Systems lock is then paired with an electromechanical key that basically has a motor in it. And you engage that motor and you press the buttons to put in your combination, and it will very, very rapidly dial in your combination into this tiny little combination lock. And it's not so much that a manipulation mechanism or a manipulation method for this is not known, it's just that it would take a very, very long time with a lot of wheels, to the point where it's kind of infeasible. We've also got things such as these registered mail counter padlocks from the US. They have these counters that increment by 1 every time the plug is turned, so they might not be the hardest thing to pick once or twice, but you're going to have to pick them 9,999 more times if you want to conceal the fact that you picked the lock. So Again, another interesting consideration that can make a lock quite high security and tamper evident. Obviously, these were for avoiding tampering with post. And then we have, unfortunately, a rather blurry picture of my favorite lock, as it happens to be, the Ratner change key safe lock. So this is a lever lock where we have a lever with these teeth on the end of it, and that engages with this this sort of gear that has the gate in it. And so lifting the lever causes the gear to turn, and the correct key causes the levers to lift to the correct heights, turning the gears to the correct amount. However, what's interesting is that when the bolt moves inwards, it also disconnects the levers from the wheels. And so the result of that is that every time you unlock the lock, it zeroes itself, and it will then key itself to whichever key you use to lock it back up again. So the idea here is clearly for banks. If the bank manager realizes that one of the keys is missing, well, it's pretty much trivial for him to change the key. He can do it in just a minute by simply unlocking the bolt and then locking it again with a new key that he knows isn't missing and hasn't been copied or tampered with or whatever. But from a picking consideration, that means that you could pick a lock like this open, but you would have a very, very hard time to then correctly lift all of the levers simultaneously to the correct matching heights when you lock the lock again. And while that might not seem like such an issue, most of the benefit of using lockpicking as an entry method over any other manipulation method or method of getting in is that it's covert. It's that people won't notice that you have picked the lock. It's for extraction normally of information, for example. Otherwise, you might as well use a destructive attack. So I find it very cool that this is basically a lock with a very high amount of tamper evidence. Finally, I'd like to give my special thanks to all of the people on this list for either their direct help by providing photos, or their encouragement, or the conversations I have had with them to help me work out how to categorize the locks in this talk. So thank you very much to all of those people in particular. And that's the end of my presentation. So if you've got any questions, I believe we will now be moving to a question and answer section.